Hello, Dr. V. This is Alex Ripple doing the gas law teach the doc. So I'm going to start with number 1. So that's the question there. So I'm starting with, looks like I'm going to be using the combined gas law because it has pressure, volume, and temperature. So it's going to be 15 times volume is 28 liters at a temperature of 205 kelvins. And that's going to be proportionate to 20 is the pressure. We'll do 20x. X is what we're solving for. It's the volume of the gas over 300. So now if I put that in my calculator, well, I can simplify that to 15 times 28. 420 divided by 205 is that. And then times 300. So 614.63 would equal 20x, and so x would equal that divided by 20. X is 30.73, which is the new, that is the new volume of the gas. So it would be 30.73 liters. All right, on to number 2. Balloon is inflated, have a volume of, well, that's what it, have that volume, temperature, volume after, so it looks like we're dealing with just volume and temperature. And I think it's going to be, never talks about pressure, so I'm going to assume that it's constant pressure, which would be the Charles law. So volume 0.75 over temperature 20 is going to be proportionate to x over 250. So 0.75 times 20 equals 15. Yeah, 15 equals x over 250. Now 15 times 250 is going to equal 3,750 will equal x. So 3,750 liters is the answer to number 2. Next is number 3. 10 liters of a gas at 3.5 atm is compressed. Well, that's the question. So I'm looking for the new pressure. So blank liters of a gas. So I have volume and pressure. So because I'm dealing with liters and milliliters, I'm going to go ahead and convert 10 liters into milliliters. So that would be, I believe it's 10 times, let me double check that. 10 liters to milliliters should be 10,000. Yeah. So 10,000 milliliters. It's going to be at 3.5 atm. Oh, wait, we're doing volume and pressure, so it's multiplied, not divided by. 10,000 times 3.5 is going to be proportionate to 473x. So 10,000 times 3.5 would get me 35,000. Which would equal 473x, and so that divided by 473 would get me 73 point, it's going to round up to 74. So X equals 74 ATM. That's the new gas. On number 4. Suppose you had... Okay, so now we're doing combined gas law again because we have all 3 variables. So it's going to be 3.15 liters. Wait, combined gas law. I'll do pressure first. So pressure is going to be 0.951 for this first part of the equation times the volume, which is 3.15 liters over 21 degrees Celsius. New one would be temperature remain constant. Oh, so I don't even measure this temperature. It just needs to be this. I didn't read it all, the whole question. So, which means that it's going to be temperature changes to 1.292 and then X for the new volume. So 0.951 times 3.15. That's going to equal 2.99565 equals 1.292x. So I'm going to divide that by 1.292. That gets me that number. So it's going to be 2.3. Yeah, we'll call it 2.32. And what's liters? 2.32 liters would be the new gas. On to number 5. Diving bell. Water level inside changes if the pressure inside equals pressure outside. Okay, so it's another combined gas law question. So initially, the pressure is 1.02 ATM times times 8.58 liters, that over 20 degrees Celsius equals, it's over 25 degrees, and then it's 1.584 ATM X volume. So 1.02 times 8.58, that divided by 20 gets me 0.43758 equals that. So if I multiply that by 25, I would get about, we'll call it 10.9395. Divide that by 1.584 gets me 6.9 roughly. So 6.9 liters. Okay, on to number 6. Wait, no, that was number 5. I think right. So next is 6. So with number 6, we're dealing with NO2, and I'm at 3.97 liters. So we know that it's 22.4 liters, which equals 1 mole at STP. So if I divide it by 22.4, I get 1.772. So now I divide that by the molar mass, which that's NO2, so that'd be 14 plus 16 plus 16. So if I multiply all that together, it's 14 plus 16 plus 16. So that's 46 times 0.1772 equals 8.1512 grams. That's number 6. All right, now for number 7. When the pressure of the gas is doubled, what is the new volume at constant temperature? What gas? It says the pressure of the gas. Pressure of the gas. Well, number 7 doesn't really give me very many details. New volume at constant temperature. Okay, so I'm just going to deal in theoreticals then. So, just talking about volume and pressure at constant temperature. So that'd be like the Boyle law. And whenever like volume goes up, pressure goes down and vice versa. So if the pressure is doubled, volume is half of the original. Alrighty. Okay, sorry, my phone died and I had to restart the video, restart the segment of the video. But I'm using Pivnert to solve 8, and Pivnert, well, when I plug on all the variables, it looks like this. And so if I simplify to this side, it's going to be P times 1.5 is going to equal 0.23 times 0.0821, which is the gas constant, times 303. That's going to get me 5.72. And if I divide that by 1.5, I get 3.81 ATM. Now for number 9. So, how many grams of chlorine gas occupy a volume of 154 milliliters and 746 torr and 25. What is torr? It's a unit of pressure. So I'm just going to use it instead of ATMs, I guess. So Cl2. So if I go to number 9, I'm looking at grams of Cl2. So if I plug that into Pivnert, I have 746 and 154. I'm just plugging all this in. My gas constant. And then 25 degrees Celsius is how many kelvins? 298.15. 298.15. That equal, wait. Okay. So this is going to equal a big number. That equals 0.0821 times 298.15. That equals 24.478 roughly times N. So if I divide this big number by that, 11,4,884 divided by 24.47, I get n equals 4, 6. Oh shoot! So this is supposed to be 0.15. 0.154. Wait. Divided by 1,000. It's supposed to be 0.154. So this number is actually supposed to be 746 times 0.154. Because I forgot to convert it to liters. So it should be under 14.84. That number divided by 24.478 equals 4.69. Yeah, 4.69. Right. 4.69 grams. That's my answer for 9. Now for 10, same deal here. I'm still dealing with PivNert. If I plug in all my numbers to the equation, I have 59.3 and 0.75. That's going to equal n. 0.0821 is my constant. Now I gotta put 33 degrees Celsius. That's going to equal 306 kelvins. Right. It's number 10. Not 59.3 milliliters, because I did not make that mistake again. It should be 59.3 milliliters equal 59.3 milliliters divided by 1,000. So 0.0593 liters. Maybe I can convert that. So on that left side, it should be 0.044475 equals 0.0821 times 306.15. It's going to equal 25.135 roughly. And if I add that number by that number, this would be really small. .0017677, if I round it right, equals number of moles. Yikes, that's very small. And that's compared to 1.08 grams of this unknown gas. So if I, with that calculation, 1.08 divided by 0.00177, that's going to equal, divided by 0.00177. So my molar mass is going to be 610.169. That's my molar mass of the mystery gas. Now for 11. Oh, the pressure. So I'm looking at with C2H6. Looks like fine. I have 2.94 grams of that. And it's ethane, which means that molar mass is 12 plus 12 plus 6. Plug that in. That gets me 0.098 moles of C2H6, which is equal to N in my PivNert equation. So if I put together PivNert, so I'm looking for pressure, so P times 0.0, where is it? 0.0 0.832 because I've converted it to liters. It was 83.2 milliliters. Equals number of moles. So 0.098 times my gas constant times how many? It's negative 24 degrees Celsius, but if I convert that to kelvins, I get 249.15. So 0.098 times 0.0821 times 249.15. P equals 2.0065. So now if I divide that by 0.0832, I'm gonna get P pressure is about 24.09 ATMs. So that's my answer. That would be the pressure of the ethane. Number 12. Determine the density of fluorine at STP. That's probably what I'm mastering now that I think about it. Determine the density of fluorine at STP. So STP is 1 ATM equals 1 ATM over 273 kelvins equals 22.4. So I did some research and I found, like on my own, and I found that to get density of something at like STP, you can use the formula, like density is pressure times mass over R times temperature. So if I plug in my numbers in that, STP. So D equals pressure would be 1 ATM because we're at STP times molar mass. This should be N. That's molar mass. Fluorine's molar mass, I believe so it'd be F2, right? Fluorine would be 19 times 2, 38 molar mass. So I really have 30 out of here because I can ignore the multiply by 1. Divided by 0.0821 times the temperature, which is 273 kelvins because we're at STP. Now, 0.0821 times 273 equal to 22.41. Where have I seen that before? Over 38. Oh, so density is, because of this equation, density is just 38 divided by 22.4. I don't even remember what this one because we're not using that consistency. So 38 divided by 22.4 would equal 1.696. Oh, that's the density. I don't know what. Would that be grams per liters? I think so. All right, now for 13. 13. 3 bottles of perfume. 10 meters in front of you. Oh, so now we're using law of diffusion because we're dealing with gases traveling at different speeds. Okay, I just start with A and B then. Well, gases with smaller mass and therefore smaller density, they're going to move a lot slower. I mean, they're going to move a lot faster than ones with higher ones. So it's just going to be A, or from slowest to fastest and increasing rate. So it's going to be C, B, A. There. Which gas will travel farther? Again with the law of diffusion. SO2 or CO2. Now if I find the molar masses of these, SO2 is going to be 32 plus 16 plus 16, so 32 plus 16 plus 16, I think it's 48. No, 64. 64, and then CO2, I'm pretty sure is just 44, but I'll double check that. 16 plus 16 plus 12, no, it's not. Yeah, 44. So it should be CO2, but I'll double check. Since CO2 is lighter. So, if I plug in, so R of CO2 over R of SO2 is going to equal square root of 64 over 44. And 64 divided by 44. So the square root of 64 divided by 44, I mean, is about 1.2. Which means that so CO2 is 1.2 times faster than SO2. So the answer is CO2 will travel faster. Next for 15. Volume of 2.5 moles. Density of this gas. Okay. So 2.5 moles. Oh, hydrogen iodine or iodide. So that should be HI. Hydrogen iodide. So 20.4 liters, and it's also equal to 2.5 mole. So I could just find, or 2.5 mole times the molar mass, which would be 1 plus 100, so it would be 128. So 128 times 2.5 is going to equal 320 grams. So 320 divided by 20.4, because it'd be mass divided by volume, it's going to get me 15.686 grams per liters is my answer. So with 16, let's check some brainstorming, but I know that this is the equation for molar mass, or for density, STP, and so if I added, or I multiplied this out, and I got 61.825 molar mass, and I noticed that that's pretty close to about like 65-ish, which is H2S. That's the molar mass of H2S, hydrogen sulfide. So I'm assuming that that is it, because it's made up of sulfur, and hydrogen is close to that mass. that molar mass. To finish off 16, it's at STP, which means that if you're to find the mass of it, you would cancel out, like you would multiply it by the number of liters, and there's 22.4 liters at STP. So it'd be just the same as this molar mass number. So I think it's just that. Now if I'm going on to 17, balloon is filled up with 6.5 grams of hydrogen 2 gas. So H2, 6.5 grams. What volume does it have? So I think I need to find the density of it. So molar mass would be 2 divided by 22.4, which would equal 2 divided by 22.4, 0.089 grams per liter will be the density of hydrogen. So how many liters does it have then? 6.5 grams. Well, well, that's density equals mass over volume. So volume would equal mass divided by density. So 6.5 divided by 0.089 would equal 73. Yeah, right about 73 liters. That's how many liters there would be of in that balloon. So now for 18. So we're trying to find R, but maybe because we have all these units, I mean, we know that STP is 1 ATM over 273 kelvins equals 22.4 liters. But maybe you were trying to plug that into Pivnert to get R. So pressure is 1 times volume is times 22.4 equals 1 mole, because 1 mole equals that. So 1 times R times 273. So 22.4 equals 273 R. And 22.4 divided by 273 gets me R equals 0.08205, which is about what we usually use, 0.0821. So there you have it. That's how we get R. Now for number 19. Wood-burning fireplace gives out 0.25 moles of CO2 each hour. Okay. Assumed each hour. How many grams? So if I set this equation up, how many grams are consumed each hour? CH4 plus O2 I need to balance that, so okay, so now it's a fluorine gas takes 25 seconds to diffuse. How many? Okay, so F2 and H2. Molar masses are, F2 is going to be 19 times 2, 38. And that's 2. So, let's find this ratio out. So, it should just be the rate of 38 divided by 2. What is, so it would be the square root of 19. It's roughly 4.336. So it's, helium is 4.36 times faster than fluorine. And so well, if I flip this, 2 divided by 30 equals 2 divided by 30, 0.229. So if I multiply 25 times 0.229, that's going to give me 5.725 seconds. The answer. Now it's 25. Temperature of the gas is increased to 1/8. The pressure is quadrupled. What will be the new volume? So we're gonna say everything is just 1 for now. Well, we'll just say P V T. Now it's gonna be temperature of the gas increased to, so it's 1/8 of T. And the pressure is quadrupled. So 4, we're just gonna say everything is 1. So 4, 1/8 will be the new volume. What will be the new volume? So P. So this is 1. 1 times 1 divided by 1 is 1. So if I multiply 1/8 equals 4p, and then 1/8 divided by 4, that will be 0.03125 equals the new, not the new pressure, the new volume. Maybe the wrong variable. So this many liters. Okay. Well, yeah, of the original. So I'll put times original. Now for 26. So 26, 20-liter containers filled with 0.5 ATM of xenon gas. What's the mass of xenon? Okay. This question doesn't really make sense. It says 0.5 ATM xenon gas and 1.5 ATM at 400. I'm not really sure what you mean by this, Doc. Maybe you meant grams instead of atms for 0.5 grams. Wait, no, because then AGP, what is the mass of xenon? Oh, 20 liters times. Yeah, I don't think, 26 just doesn't make sense, Doc. You're gonna have to revise that. Variables don't make sense. I think there must be a typo or something, but I don't think I can solve that. I'm gonna move on to 27. Okay, so 27 is just the first half of it is what I already did earlier. So you can already look back at 11. Which question did there's a question where I calculated what R was. So R, there it is. So based off of this data, I know R is 0.0821. So I know R is 0.0821. And it was because 22.4 equals R times 273. So R equals 0.0821. Now, at what temperature will chlorine gas have a density of 1.48? Well, at STP, we know that chlorine gas would have a density of, well, Cl2 is 70. So 70. So 70 divided by 22.4 would get me my density at ATP. So 70 divided by 22.4, 3.125 grams per liters at ATP. Now I have to figure out what it'll be when it's 0.57. So 3.125 is my density. Occupies volume of at 0.57. So this would be times 1, but that doesn't matter. And then it's divided by, oh yeah, 273 kelvins is ATP. That's going to be proportionate to the temperature we're solving for, with 1.48 times 0.57. So if I cross multiply, 3.125 T is going to be equal to 273 times 1.48 times 0.57. Which would get me 230.028. Now divide that by 3.125, and T would have to be 73.7. must be 73 kelvins. That is the answer. Now for 28. Okay, so now I'm doing this tire question. That's run air. Notice it doesn't look as full as before. Assuming volume is constant, I noticed that. And volume is constant would be... Well, let's just do combined gas law for now. So... gonna convert these. Well, it should be fine in Celsius. So what is the pressure in your tire assuming volume? So it starts off as 240 kPa. 241. So we're solving for this pressure. I'm going to convert these to kelvins. So 4.4 Celsius would be 277.55 kelvins. And then I think it was negative 12. No, 12. Negative 11. 11.1. Negative 11.1 degrees Celsius would be 262.05 kelvins. We're solving for X kPAs. So take that out. Or cross out these. They all cancel out. So cross multiply 241 times 262.05 would be 600.05 equals 241x. So divided by that would be x equals, oh, well, just gonna be, these cancel out. Oh, I did this wrong. This would be 277.55x. So divided by 63154.05 divided by 277.55. That's going to equal 200. That's going to equal that. And put that on the end. That's the new pressure. All right, now for 29. A gas fused 4 times faster than an unknown gas. What is the molar mass of a gas? So a gas is 4 times faster than that. Look for the molar mass of it. So molar mass of into H4. That's going to be 14 plus 14 plus 4. 32. 32 is the molar mass. And it's 4 times faster. Wow. 4 times faster than. Okay, so 32 divided by x would be what I'm looking for. What is the molar mass? Equals 4. So what makes that equal 4? Well, root of 32 by itself. I could do 32 x equals 4 squared would be 4 times 4. 16 times x. 32 equals 16x. Look at this coming. Which means x would equal 2. So 2 is the molar mass. The unknown gas, which I know is gotta be H2. Alright. And I'm gonna move on to the next page. Okay. 50-liter container designed to withstand a maximum pressure of 22.5. The container is holding 11.2 moles. Think through this. Temperature that the container can withstand before bursting. Um, 50-liter container. What is the max pressure? Well, I'm going to start with just finding out how many. Well, N2 would be nitrogen gas, and there's 11.2 moles. Well, never says ATP. I guess I'm looking for Pivnert. So something. So P. Well, pressure is 22.5 times 50, and then it equals Pivnert. So number of moles, 11.2 moles times 0.0821 time, because that's R. Then T, temperature. So 22.5 times 50. 11 to, okay, and then 11.2 times 0.0821 equals 0.91952 T. Now I'm going to divide that by that. And then I get that T is 2.46. And that, I'm assuming, is going to be in kelvins. So that is my answer for 30. It's pretty high. Alright, next is 31. Calculate R. Well, I already did that twice, actually. But I know that I'll do it again just for, well, earlier in the video I calculated R twice with this logic. So I know that R is 0.0821. And wait, this is just the same as earlier. Dr. V, you put the same question in here twice. Well, number 31 is exactly the same as number 27. So, number 27, I look back. Number 27, I got 73.7 kills. The answer is number 27. Yeah, that's what I got. What temperature? Okay, last question, number 32. Okay, what temperature will bromine gas at point of density of that? Okay. So Br2 has a molar mass of 80, or 160 mole mass. So density. So if I use ideal gas law, should be 0.85 times 1.48 over wait, that's not right. It's not changing. Okay, so continuing with 32, I know that for the ratio, ATP ratio would be, well, $273. Well, and then bromine would be 160 divided by 22.4. So 7.14 is this ratio. Now, I'm looking for 0.85 times 1.48 over x. That's what we're solving for. So 7.14x equals 0.85 times 1.48 times 273. 343.43. Divide that by 7.14. And then x equals 48.1 kelvins. Alrighty. Well, Doc, that is all the questions solved. Thank you for watching this, and thank you for creating this assignment for me to show what I learned. Thank you for continuing to balance this equation. 4, 3. Okay, this is my balanced equation right here. And how many grams of oxygen and gas are consumed each hour? So we'll take out the hour of the constant by just saying that it's 0.25 moles of that. Moles of CO. How many grams of oxygen gas are consumed each hour? So how much of that? So 2.5 mole. The ratio here is, it looks like, so I need to, it's multiplying by 3 over 2. So 0.25 times 3 over 2, that would equal 0.375 moles of O2. And then 0.375 moles of O2. Well, now I need to multiply that by the molar mass to get it back to grams. And that's what it is. Yeah, that's what we're solving it. It's in grams. So 0.375 times 32 gets me 12 grams per hour. Okay, now for 20. How many liters of nitrogen will be produced from 38.9 liters of NH3 at STP? Okay, how many liters? Okay, so it's the STP. This is the equation that we have. It's a decomposition equation. 3, so 3 and 2. Alright, that's my balanced equation right there. Liters, so there's 38.9 liters of this at STP. So divided by that, so if I have to divide that by 22.4 would get me, let me double check that. Yeah, that would be getting me moles. So 38.9 divided by 22.4 gets me 1.737 moles of NH3. Then I multiply that because I'm solving for how many liters of nitrogen. So I have to divide this by 2 to get that mole ratio. So that would be 1.737 divided by 2 gets me 0.8685 moles of N2. Multiply that by 22.4 would get me my answer, which is 19.45 roughly. And that's 19.45 liters. Now for 21. Sample of gas at 200 K occupies the volume to a temperature. I believe it's all proportionate. So, starting with kelvins over 2 times 10. It's a double both the volume and pressure. If I multiply that by 2. It just had to be 400 because that would multiply everything by 2. So the answer is 400. 400 kelvins. Now for 22. So 2 liters oxygen. What is the temperature? Temperature's raised. Final pressure. So this is another combined gas law. So it looks like it's pressure times volume 2 liters over 273 equals, looks like it's 546 under P times 1. So 4 divided by 273 0.01465 equals P divided by 546. If I multiply that by 546, well, that just gives me 8. So P equals 8. Right? So 8 ATM. The final pressure. Okay. Now 23. Gas occupies 10 liters. Two ATM and 300 K. So ATM would be 273, and then it's just 1 times 10 liters. In parentheses times 1, and then 302 ATMs. Wow. Cross multiply here. 273 times 2. So 546x equals 10 times. Equals 3,000. 3,000 divided by 546. X equals 5.49. X is equal to, yeah, liters. All right, now on to 24.